Hi, this is Rob Carolina, and this is the third in a series of three talks about cybersecurity password combinations. This one is specifically about the impact of password exclusion policies on the size of key space, or telling end users they must include at least one special character in their password may be a bad idea. Now, I did these talks because I'm interested in relative strength of passwords, and password strength is related to the number of possible password combinations, the size of key space. I wanted to get a more intuitive feel for how to calculate that size and to understand how policies influence the size of the key space. But I'm a lawyer, not a mathematician, and I wanted to be able to understand this without going to a class in combinatorics. I figured that if I wanted to get a better feel for this, maybe others want the same. So in talk number one, I talked about basic key space calculations. Talk two, I think, is one that will be of significant interest to people who work in security who are not mathematicians, and that is calculating the change to the size of key space caused by password exclusion policies. But now, in Talk 3, I want to consider the impact of some password policies on the size of available key space. So at the end of Talk 2, we came up with this conclusion, and that is, if you assume a constant password length of x, and the password is comprised of 4 sets of available characters with a mandatory minimum of 1 from each set, and the sets are uppercase letters, 26 of them, 26 lowercase, 10 numerals, and 5 special characters. The resulting size of the key space of the permissible key space is expressed by this formula. Now, the total key space, before we impose exclusion rules, would just be 67 raised to the power of x. Everything else in this formula is a function of saying that we are not allowed to use passwords unless they have at least one uppercase, at least one lowercase, at least one number, and at least one special character. But where we left talk 2 is, well, what does this even mean? What does this mean for password security? First of all, well, what if we just eliminated special characters entirely? What would that formula look like? Okay, so the revised policy, let's assume, looks like this. Each password must include at least one lowercase, one uppercase, one numeral. So a number of passwords are not allowed. Here's some examples of those. And repeating the methodology that I used in talk number 2, I'm not going to go through each step, but I will show you the bottom line calculation. First of all, in talk 2, remember we were talking about passwords that draw from 4 available and mandatory sets. Well, now we're only dealing with 3 sets. So I drop out of the Venn diagram all the special characters. That leaves us a slightly more traditional Venn diagram of 3 intersecting sets, which means 7 possible regions. The number of passwords that comply with our new policy is the number of passwords that live in region J. So we want to count every password that lives in region J, and we do that by excluding the passwords that live in all the other regions. Well, when you sit and go through the calculation, laboriously one step at a time, what you find is that this is the formula for calculating that number. 62 to the x, which of course is all of the passwords put together, but then we exclude, in the second set of calculations there, we exclude everything that's not a number, not an uppercase, doesn't have a number, doesn't have an uppercase, doesn't have a lowercase. But then we have to re-include, because we've double counted, we need to re-include and reincorporate things that consist of only lowercase, only uppercase, and only numerals. And the bottom line is this long sum. So what's the difference? Let's compare. 3 sets of characters, lower upper numeral. 4 sets of characters, lower upper numeral special. And the password policy says, we will exclude, we will not let you use a password unless you've taken at least one from each set. Well, we bring in the formulas that we've already calculated, and we find that the size of the key space when we have these three sets of characters, S3, is the equivalent of that long equation on the left, and S4 is that long equation on the right. Now, by the way, if you got some spare time and you want to have some fun, just to prove to yourself that this works, have a look at the 4-set character equation that S4 figure, and ask yourself, what would happen if I had only a password of length 3? So what if x equaled 3, less than the number of sets? Do that calculation and see what comes up, and then do it with x equals 2 or x equals 1. You'll be you should be able to predict what happens, but you might have fun anyway. Back to our story. Let's run the figures. Let's just run the numbers for a password of length 8. Okay, x equals 8. What do we do? Well, for S3, we plug in the numbers into the formula, and we discover that there are 1.597 times 10 to the 14th combinations, 47.182 bits. Okay, not bad going. Now what happens when we add the 5 special characters? In other words, we appear to be increasing the complexity of the key space because we're adding more characters. Okay, S4 now equals 1.207 times 10 to the 14th. Wait a minute. That's 46.779 bits. That's actually less than the 3 sets. Well, it turns out that's not a math error. That is what happens. By introducing a mandatory special character requirement, we have actually reduced the size of the key space. Now, admittedly, not by very much, but it's a reduction in the key space. Well, what happens if we try some passwords of different lengths? Let's first simplify this so that we're only reporting bits. So clean the slide up a little bit. What about a password of length 9? 9 characters long. Okay, in this case, S3 equals 53.230 bits, and S4 equals 53.105 bits, and darn it, we've done it again. We've actually reduced the size of the key space. Well, is this going to continue forever? No, actually it won't, so give me a moment, and we'll try passwords of length 10. S3 equals 59.255 bits, and S4 equals 59.376 bits. Well, hooray! We've finally actually increased the key space by adding the special character requirement. Now, in each of these cases, there is a bit of a difference between them. But that difference is not what I would describe as too tremendously big. So here's the impact of adding special characters from set Z on the size of the key space, given all the other parameters that we've said. I think there's maybe a lesson to be learned here, or at least an observation to be made, and that is password policies that move in this direction, which is they say, well, currently we allow users to use upper and lowercase and numerals. Let's chuck in a couple of extra special characters. That doesn't really seem to be helping very much, at least not on the pure math of it. But notice what is having an enormous impact on the size of the key space. And that's if we move up the chart, if we make the password longer. So even when we're only drawing from 3 sets, every time we lengthen the password by 1 extra character from 8 to 9, we've added more than 6 bits onto the size of the key space. And by bringing it out to 10, that's another 6 bits. So the gain that we get from shifting from 8 to 9 length passwords, password of length 8 moving to password of length 9, is enormous, as opposed to actually slightly damaging the size of the key space by adding in a few special characters. Let's look at this a little differently. You might be saying, hey, Rob, why did you just choose 5 special characters? I mean, what if we change there? All right. Looking at our Venn diagram again, we start with a password policy that draws from only 3 sets, lowercase, uppercase, and numerals, and we only allow passwords from the intersection of all 3 of these. Only passwords from region J are allowed because you have to have at least one of those characters in the password. Now, what if we add a mandate to include a 4th set of special characters, but we have more special characters? We reintroduce the 4th set into our Venn diagram. We're now looking for the intersection of 4 sets, which is region H, but we're going to allow more special characters. Our formula for calculating the size of the key space is still going to require the sum of 15 components, and the exponent of each of those is still going to be x, the length of the password. The base of each of those numbers in the calculation must now be recalculated because we've changed the size of the key space in total and we've changed the size of one of the sets. Each of those base numbers was calculated by reference to the number of characters in the other sets. So here's a summary of what happens. If we assume again a constant password length of x, and it's comprised of 3 mandatory sets with a minimum of 1 from each, uppercase, lowercase, and numerals, then adding a mandatory 4th set of special characters from set Z, and let's call the number of special characters in that set zeta. It's going to have the following impact on the size of the permissible key space measured in bits. So here, if you look at the left-hand side of the chart, number of characters available, that tells us how many special characters are there, or how many special characters will our system allow in a password. And then the password length starts at a short password of 6 and goes all the way out to 14 characters long. As you can see, in a lot of the places, still, adding those special characters will reduce the size of the key space. Now, just to orient you, the preceding slides calculated with the impact of adding special characters when there were only 5 special characters available. I told you that for a password of length 8, adding a set of 5 special characters and requiring every password to draw from at least one of those reduced the size of the key space by about 0.4 bits. Whereas a password of length 10, you finally start to get a little bit of an increase in the size of the key space, but not much. So if we get up to like 7 or 8 special characters, then at least in theory, we're starting to have a little bit of an impact on the size of the key space. But I want to draw your attention especially to the bottom of this chart. What if there are only 1 or 2 special characters available? Now, why am I focusing there? That's because when password policies tell end users that end users must insert at least 1 special character, we know from experience that end users don't always draw from a wide variety of them. In fact, there are a couple of special characters that are well known for being more popular than others. And if I were an attacker and I were to make a reasonable guess that my target probably only uses 1 of these special characters in their passwords, then effectively I can structure an attack on the assumption that only 1 special character is available to the end user, and now we've very significantly impaired the size of the key space. Okay, let's go back and look at our calculation for what happens when we only used 3 sets. Remember that when we only have 3 sets, uppercase, lowercase, and numerals, we only have 7 regions in the Venn diagram, and it's only the passwords in region J that will comply. We calculated that the number of things living in this region J was about 47.812 bits when the password is of length 8. Let's hold on to this calculation because we might want to compare it to something. We add a mandate to include a 4th set made up of special characters. We bring the special character set back into the Venn diagram. We now have 15 regions. Now the only passwords that comply are the passwords that live in region H. The count of the things that live in region H is about 46.779 bits. Let's think for a minute. What if we only required users to select from 3 out of these 4 sets? What if an end user said, I don't want to use special characters? And our response is, oh, that's okay, so long as you have a lowercase, uppercase, and a numeral. Or users said, I don't want a numeral. Well, so long as you have lowercase, uppercase, and special, we can live with that. That means that acceptable passwords now live in 5 regions, regions C, G, H, J, and M. And we want to know how many passwords live in those 5 regions. Well, Using the methodology introduced in talk number 2, with some modifications, we can calculate that the total count of passwords living in those 5 regions is 48.298 bits. So this means that if we want to increase the size of the key space, if we want to increase the potential number of passwords available when we add special characters, maybe the way to go about it is by telling end users, here's some special characters that are also available. You don't have to use them, but you can. And suddenly we find our key space growing once again. Now, if you're interested, if we change the length of this password, let's say down to 7, here's the calculated key space for each of these calculations. If we bring it up to 9 or 10, once again we see that telling users they only have to select from 3 out of the 4 available sets allows us to increase the size of the key space rather comfortably. So what have we learned from all of this? Well, in terms of mathematics, we've learned that calculating the raw size of key space isn't really that difficult. Size of the key space is equal to the number of characters available raised to the power of the length of the password. We've also discovered that calculating the size of permissible key space after we impose a series of exclusionary rules is more difficult, but it can be understood using pre-university mathematics and Venn diagrams. That's what talk number 2 was about. In terms of lessons learned for cybersecurity, we've learned in this talk number 3 that increasing the key length has a greater positive impact on the size of the key space than adding special characters to pre-existing sets of lowercase, uppercase letters and numerals. We've also learned that introducing and mandating special characters in passwords can actually serve to reduce the size of key space, especially when password length is less than 10 characters and there are fewer than 7 special characters available to use. We've also learned that the way users react to a special character mandate can significantly magnify the loss of key space. Now, looking forward, what else should we consider? What haven't we really talked about? Well, end user behavior is typically non-random. And because end users act in a non-random fashion, they tend to create what we can think of as junk passwords. Passwords that are easy to test for, easy to crack. Things like routine combinations, character substitution strategies, numeric patterns, or reordering behaviors when we tell end users they have to change their password frequently. That leads us to this conclusion, that the number of acceptable passwords is actually less than the size of the key space that we calculated. How much less, and what should we do about it? Well, maybe that should be the subject of another talk. If you enjoyed this video, please hit like and leave a comment below. My thanks to the Information Security Group, where I teach legal and regulatory aspects of cybersecurity, especially for comments from Professor Chris Mitchell and Darren Hurley-Smith. I'm grateful for comments from my test audience, Gabe Komick, Dan Hauser, Sonia Millivac, Carolina, Mark Milton, and Alec Muffett. And a special thanks to Professor Fred Piper for introducing me to the idea of combinatorics.